Okay, let's now switch gears and turn our attention to aerobic exercise program design. Now, as I already mentioned, most athletes as well as non-athletes would be better served by constructing their own training regimen based on a good working knowledge of sound training principles and an understanding of their own physical limitations and needs. Now, what successful aerobic endurance athletes have in common is a training program designed to enhance their strengths and improve their weaknesses. So, in terms of the aerobic exercise program design, first step really is to do a pre-evaluation of those factors related to aerobic exercise performance, so VO2 max, lactate threshold, and exercise economy, and use that information to identify strengths and weaknesses to generate or design a specific training program. So, step one is going to be choosing the exercise modality. And for aerobic exercise, we're primarily focused on cycling, running, or swimming. And what we know is that the more specific the training mode is to the sport, the greater the improvement in performance we expect to see. Some athletes may choose to do what is known as cross-training. And the benefits of cross-training are numerous. It includes maintaining fitness during reduced training loads, reduced risk of suffering an overuse injury, as well as some aerobic athletes may choose to do cross-training to maximize performance, particularly if they're a multiple event athlete such as a triathlete. What's important to note here is that the cross-training modality, should be similar in intensity as well as duration as the primary mode in order to maintain adaptations that have occurred as a result of training. This is particularly important in those single event athletes, such as those that only do swimming, cycling, or running. Next up, we have training frequency, which is going to depend heavily on the interaction between exercise intensity as well as duration, but also the training status of the individual, the athlete's age, other time commitments, and the specific sport season that the athlete or individual is currently in. Now, if we look at this table here from the NSCA textbook showing sport-specific objectives and program design assignments. So we'll talk more about these sport seasons when we talk about resistance training program design. But for most athletes, they have 4 distinct sport seasons. So the off-season, pre-season, in-season, also known as the competitive season, and the post-season, also known as the active rest period. So you can see the various aerobic exercise objectives for each one of the sport seasons. We'll come back to those later. The suggested frequency, so in terms of sessions per week or days per week, with a higher frequency of training during the off-season and the pre-season relative to the in-season, which again, this is primarily when practice as well as racing is occurring. And also we see higher frequency in these 3 previous seasons compared to the postseason or the active rest season. And we also see in the different sport seasons the trade-off between duration of exercise and intensity of exercise. So in the off-season, an athlete is attempting to develop some sound conditioning base, high frequency of training, performed at a longer duration but a low to moderate intensity. Whereas if we get into the end season, depending on the specific athlete and event, if they're training, they may have a short duration of training, performed at a low intensity, but obviously during the actual competition itself, that distance is going to be whatever the race is, performed at a high intensity in order to try to win the event. So recovery is also very important when we're talking about designing a training program. So this recovery includes proper rest, rehydration, restoration of fuel sources such as muscle glycogen. But recovery from individual training sessions is going to be essential if the individual is to derive maximum benefits from the subsequent training session. Next is training intensity. And what we know based upon the specificity principle is that adaptations are specific to the intensity of training. So for example, high intensity aerobic exercise increases cardiovascular function and allows for improved oxygen delivery to the working muscles. So there are a number of adaptations occurring within the heart as well as within the muscles that allow for greater delivery and thus utilization of oxygen by the exercising skeletal muscles. Another benefit of increasing aerobic exercise intensity is that it also may recruit type 2 muscle fibers. So what we know based upon the size principle is that exercise activities that recruit the type 2 muscle fibers result in adaptations within those specific muscle fibers. Those adaptations may include increases in capillary density and increases in mitochondria density. Now, if the intensity is too low, the training intensity is, say, way too low in order to induce a stimulus, therefore we have no overload and we would expect little to no adaptations to occur. Therefore performance would not improve. If the intensity is too high, though, then fatigue and premature exercise cessation may occur as a result of that. Now, in terms of monitoring exercise intensity, the most accurate methods occur within the laboratory, and that's by monitoring VO2 or oxygen uptake and blood lactate levels during exercise. However, as most of us are aware, not all athletes have access to sophisticated equipment within the laboratory. Therefore, the most common measure of exercise intensity, particularly during aerobic exercise, is using one's heart rate. So we look at this table showing the relationship between VO2 max, what we call heart rate reserve, and maximum heart rate. We see particularly there's essentially a one-to-one relationship between percent VO2 max and percent of one's heart rate reserve, whereas there's a little bit more of a disconnect between percent VO2 max and percent of one's maximal heart rate. Again, we would use this a lot, using heart rate to prescribe exercise, using this as a measure of exercise intensity, which is a very important component of exercise prescription. So let's do some calculations here showing how we can use heart rate reserve first to determine aerobic exercise intensity. So this is referred to as the Karvonen method or the percent heart rate reserve method. So most of us are familiar with how to calculate age-predicted max heart rate. That's simply 220 minus a person's age. And this is a good index of a person's predicted or max heart rate if lab testing is not available to directly determine a person's max heart rate, let's say during a maximal treadmill test. Heart rate reserve is simply basically max minus rest. So we take age-predicted max heart rate minus the resting heart rate. It gives us heart rate reserve. And then we calculate what we call a target heart rate, where we take heart rate reserve times the exercise intensity. So this is the intensity of exercise we want the athlete to work at. Then we have to add back the resting heart rate. This is an important step that a lot of people forget about. And we do this calculation twice to determine what is called the target heart rate range. So if we look at myself as an example here, I'm 38 years old, have a resting heart rate of approximately 55 beats per minute. So we take 220 minus my age, that gives us my age predicted max heart rate of 182. Heart rate reserve is 182 minus 55, so max minus rest gives us 127 beats per minute. And let's say you wanted me to run at an intensity corresponding to 70 to 80% of my VO2 max. If we look at here for percent heart rate reserve, 70 to 80% of heart rate reserve corresponds exactly to 70 to 80% of my VO2 max. So to do that calculation, we take the heart rate reserve times 0.7, again, which is the fraction of 70%. Remember to add back the resting heart rate, and that gives us the lower end of the range, 144 beats per minute. Do the same thing for the higher end, 80%, 127 times 0.8, add back the resting heart rate, and that gives us an upper end of the range of 157 beats per minute. Now if we use the percent of max heart rate method, we get slightly different numbers. This one's very similar to heart rate reserve, except we're not taking into account the person's resting heart rate. So again, we're calculating age predicted max, 220 minus the person's age. We're calculating their target heart rate as the age predicted max heart rate times exercise intensity. And we do this calculation twice to determine the target heart rate range. So looking back at my data here, 38 years old. Again, for this method, we're ignoring the resting heart rate. That's not taken into account here. So age predicted max 182. We take the 182 times the 70%, 0.7, gives us 127 beats per minute. And then my max times 80%, the upper end of that range is 146 beats per minute. And if we compare that with the heart rate reserve method, the range here for the percent of max heart rate method, 127 to 146, whereas with heart rate reserve, slightly higher values of about 144 on the low end to 157. So this should show you here that if we decide to use the percent of max heart rate method, we may actually underestimate exercise intensity. So I would say it's more appropriate in terms of assigning exercise intensity to an individual to use the percent of heart rate reserve method, because it more closely matches up with one's percent of VO2 max. The next step is exercise duration. So we see various types of aerobic endurance training here, and we'll come back to those later on in another video. We'll talk about each one of these training types in detail. You see how the frequency per week that's suggested here. But what we look at in this table is really a trade-off between duration, also known as the work bout portion, and the intensity of exercise. We know that the duration of the training session is often influenced by the exercise intensity. Therefore, the longer the exercise duration, the lower the exercise intensity. So if we look at long, slow distance training, that's performed for a longer duration, but at a lower intensity compared to something like interval training, which is performed for a shorter duration, but a higher intensity, so closer to one's VO2 max. We also have to talk about aerobic exercise progression. We know that once an individual begins an aerobic exercise training program, they need to continue and progress the program to either maintain or increase their aerobic exercise performance, which is the goal for many athletes. So progressing aerobic exercise training involves increasing the frequency, intensity, and/or duration of training. It's suggested that increases in frequency, intensity, and/or duration should not increase by more than 10% each week. So a more conservative approach here to avoid fatigue and overtraining. This will be an example of progression over the course of 5 weeks. So starting week 1, 4 times per week at about 70 to 85% of heart rate reserve for 40 minutes per session. The next week we're increasing the frequency as well as the duration of each training session. Week 3, we're doing 3 times per week at 70 to 85% for 40 minutes, but also adding in 1 times per week at a lower intensity, but for a longer duration. Week 4, back to 4 days per week at 70 to 85%, increasing the duration here, and also adding back in that 1 day per week at a lower intensity, but for a little bit longer duration. And then finally, week 5 here, basically the same as week 4, but just increasing the duration of this 1 day per week of this lower intensity training bout. Now, in some cases, it may not be feasible to increase frequency or duration. It depends on the athlete's schedule, as well as other time commitments, other training they may be doing. But in that case, progression can occur with a manipulation of exercise intensity. However, it is important, and something we'll talk about in a later topic, is that progression of intensity should be monitored in order to prevent a condition known as the overtraining syndrome, which is characterized by marked decreases in exercise performance.